Second Unit. The Circulation. Chapter 3. The Normal Electrocardiogram. Study of electrical properties of the myocardium. Textbook. Richard Klabunda, Ph.D. Cardiovascular Physiology Concepts. New 3rd edition. Published by Walters Kluwer, 2021. Revised November 2, 2023. This lecture can be found on the Normal Physiology course website. Volume Conductor Principles and ECG Rules of Interpretation. The electrocardiogram uses electrodes on the surface of the body to measure the electrical activity of the heart. It is possible to place electrodes on the body surface to measure cardiac electrical activity because the body acts as a conductor of the electrical currents generated by the heart. What do these electrodes actually measure? If a piece of living ventricular muscle is placed in a bath containing a salt solution to conduct electrical currents, and electrodes are placed in the bath on either side of the muscle, no potential difference would be recorded between the two electrodes when the muscle is in its polarized, resting state, top panel of figure at right. The reason for this is that the outside of the cells is positive relative to the inside because the resting membrane potential is about -90 MV. Therefore, no currents will flow along the surface of the muscle and through the bath. If the left side of the muscle is stimulated electrically to induce self-propagating action potentials, a wave of depolarization would sweep across the muscle from left to right, lower panel. Midway through this depolarization process, cells on the left, depolarized cells, would be negative on the outside relative to the inside, while non-depolarized cells on the right of the muscle would still be polarized, positive on the outside. There would now exist a potential difference between the positive and negative electrodes. By convention, a wave of depolarization heading toward the positive electrode is recorded as a positive voltage, upward deflection in the recording. After the wave of depolarization sweeps across the entire muscle mass, all the cells on the outside are negative, and once again, no potential difference would exist between the two electrodes. The entire process of depolarization and repolarization is depicted in the animated model to the left, which is representative of the electrical events that occur in the atria. In the resting, polarized state, no potential difference is measured between the positive and negative electrodes, i.e., isoelectric, flat red line. When the left side of the tissue becomes depolarized, representing firing of the SA node, a wave of depolarization begins to spread across the atria. During this time, some muscle mass temporarily remains positive on the outside, polarized, and while some is negative, depolarized. Thus, there is a separation of charges which causes a potential difference between the two electrodes. Because the wave of depolarization is moving toward the positive electrode, by convention, a positive voltage, upward deflection, is recorded. The voltage reaches its maximal positive value when half the tissue is depolarized. Once the entire atrial mass is depolarized, all cells negative on the outside, there is no longer a potential difference and the voltage is zero just as it was in the polarized state. When repolarization occurs, starting first with the left side, SA nodal region, then moving across the atria, there will once again be both positive and negative charges on the surface of the atria, but this time, the negative charges will be closest to the positive electrode. The wave of repolarization sweeping across the atria away from the negative electrode and toward the positive electrode causes, by convention, a negative voltage, downward deflection, to occur. Finally, when all the cells are repolarized, the measured voltage difference will once again be zero until another wave of depolarization occurs. A similar process occurs within the ventricles, with one major difference: repolarization normally occurs in a direction opposite to depolarization. In other words, the last cells in the ventricle to depolarize are the first to repolarize. This results in a positive recording as the ventricles repolarize as shown in the animated model to the right. Several important observations and rules emerge from these volume conductor considerations. 1. A wave of depolarization traveling toward a positive electrode produces a positive deflection in the ECG trace. 2. A wave of depolarization traveling away from a positive electrode produces a negative deflection. 3. A wave of repolarization traveling toward a positive electrode produces a negative deflection. 4. A wave of repolarization traveling away from a positive electrode produces a positive deflection. 5. A wave of depolarization or repolarization traveling perpendicular to an electrode axis produces no net deflection. 6. The instantaneous amplitude of the measured potential depends on the direction of the mean electrical vector relative to the recording electrode lead axis. 7. The voltage amplitude is directly related to the mass of tissue undergoing depolarization or repolarization. The first 4 rules are derived from the volume conductor model described above. The 5th rule is also based on volume conductor principles and could be modeled by placing the positive and negative electrodes midway on the top and bottom surfaces of the tissue instead of on the ends. In this case, the positive electrode would first measure a positive voltage as the wave of depolarization transverse the tissue from the left edge to the midpoint, toward the electrode, and then the electrode would measure a negative voltage as the wave moved away from the electrode to the right edge. The 6th rule considers that at any given time during depolarization in the atria or ventricles, there are many waves of depolarization traveling in different directions relative to the positive electrode. The recording by the electrode reflects the average, instantaneous direction, and magnitude, i.e., mean electrical vector, for all the individual depolarization waves. The 7th rule simply states that the amplitude of the wave recorded by the ECG is directly related to the mass of the muscle undergoing depolarization or repolarization. For example, when the mass of the left ventricle is increased by hypertrophy, the voltage amplitude of the QRS complex, which represents ventricular depolarization, is increased in certain leads. ECG vector analysis. What is a vector? The electrical fields produced by the heart can be effectively described using vectors. A vector is a directed line segment. It has an initial point and a terminal point. A vector is drawn as a line segment with an arrow at the terminal point. A vector has magnitude, how long it is, and direction. Vectors. The same vector can be placed anywhere on the coordinate plane and still be the same vector. The only 2 bits of information a vector represents are the magnitude and the direction. Since neither of these specify a starting or ending location, the same vector can be placed anywhere. To illustrate, all of the line segments below can be defined as the vector with magnitude A and angle 45 degrees. Projection of the vector on the axis. Coordinate systems in the ECG. Einthoven's triangle. Einthoven's triangle. Einthoven's triangle is an imaginary formation of 3 limb leads in a triangle used in electrocardiography. The shape forms an inverted equilateral triangle that produces zero potential when the voltages are summed. It is named after Willem Einthoven, who theorized its existence. Axes of Einthoven bipolar extremity leads. Do not confuse following items. Electrode is a part of ECG device, which is placed on, or inside, patient's body to record the electric potentials. Lead is a junction of parts of human's body on which potentials are registered and measured. Axis of leads is an imaginary straight line that connects active and passive poles of leads, electrodes. Einthoven's triangle. First lead, this axis goes from the right arm, negative electrode, to the left arm, positive electrode. Second lead, this axis goes from the right arm, negative electrode, to the left leg, positive electrode. Third lead, this axis goes from the left arm, negative electrode, to the left leg, positive electrode. Einthoven used these measuring points, by immersing the hands and foot in pails of salt water, as the contacts for his string galvanometer, the first practical ECG machine. Axes of Goldberger augmented extremity leads in Einthoven's triangle. Hexaxial reference system. Hexaxial reference system. Also known as Cabrera coordinate system, Bailey coordinate system, hexaxial reference system, is a convention to present the extremity leads of the 12-lead electrocardiogram, that provides an illustrative logical sequence that helps interpretation of the ECG, especially to determine the heart's electrical axis in the frontal plane. Formation of the hexaxial reference system of limb lead. Let's divide the lead axes into positive and negative parts and unite their 0 points at one point arbitrarily chosen in space. Let's call the created coordinate system a 3-axis coordinate system according to Cabrera, or Bailey. We have already created a similar coordinate system for Goldberger leads, see figure on the right. Now we will combine the 3-axis coordinate systems for the Einthoven leads and for the Goldberger leads into a single 6-axis coordinate system according to Cabrera, Bailey. The hexaxial reference system showing the orientation of each lead. Axes of the Wilson unipolar chest leads. Axes of the Wilson unipolar chest leads. Enlarged picture. Use of vectors to represent electrical potentials. Let us assume that, as a result of the electrical activity of the heart, at some point in time, the potentials shown in the figure were formed on the surface of the patient's body. On the right hand, -1 mV, on the left hand, 0 mV, on the right leg, -3 mV and on the left leg, +2 mV. Let's find out what the electrocardiograph shows at this moment in the Einthoven leads. Lead 1 is the voltage between the left arm, L, positive, active electrode, and the right arm, R, negative, passive electrode. Lead 1 equals L minus R. Lead 2 is the voltage between the left leg, F, positive, active electrode, and the right arm, R, negative, passive electrode. Lead 2 equals F minus R. Lead 3 is the voltage between the left leg, F, positive, active electrode, and the left arm, L, negative, passive electrode. Lead 3 equals F minus L. Thus, in lead 1 the potential difference is +1 mV, 0 minus -1. In lead 2 the potential difference is +3 mV, +2 minus -1. In lead 3 the potential difference is +2 mV, +2 minus 0. The potential on the right leg, electrode N, is not used in the calculations. The obtained values in the Einthoven leads correspond to the values of the projections on the axis of the leads of the Einthoven triangle of the instantaneous average vector. From the projections of this vector we can find the instantaneous average vector itself. Instantaneous mean vector synonyms. Mean electrical vector. Resultant vector in the heart at any given instant. Ventricular depolarization and electrical axis. Sequence of ventricular depolarization. The figure shows the instantaneous average electrical vectors that occur sequentially during ventricular depolarization. In this model, each of the 4 vectors is depicted as originating from the top of the interventricular septum, just below the AV node. The electrode placement represents lead 2. During ventricular activation, impulses are first conducted down the left and right bundle branches on either side of the septum. This causes the septum to depolarize from left to right, as depicted by vector 1, panel A. This vector is heading slightly away from the positive electrode, to the right of a line perpendicular to the lead axis, and therefore will record a small negative deflection, Q wave of the QRS. About 20 milliseconds later, the mean electrical vector points downward toward the apex, vector 2, and is directed toward the positive electrode, panel B. This produces a very tall positive deflection, R wave of the QRS. After another 20 milliseconds, the mean vector is pointing toward the left arm and anterior chest as the free wall of the ventricle depolarizes from the endocardial to the epicardial surface, vector 3, panel C. This vector records a small positive voltage in lead 2. Finally, the last regions to depolarize results in vector 4, panel D, which produces a slight negative deflection, S wave, of the QRS. The shape of the QRS complex is different for each of the limb leads because each of the leads will see the sequence of depolarization vectors from a different perspective, see axial reference system. The animated figure shows how the QRS complex appears for lead AVF and lead 1. The positive electrodes for these 2 leads are at +90 degrees and 0 degrees, respectively. In this illustration, the mean electrical axis, see below, is about +60 degrees. Note that AVF shows a large net positive QRS. There is no Q wave because septal depolarization is not directed away from the lead, see ECG rules. The R wave is very positive because early ventricular depolarization is largely directed toward this lead. The S wave is also present because the terminal depolarization of the upper wall of the left ventricle is directed away from AVF. In contrast, lead 1 has an initial Q wave, septal depolarization is directed away from the lead, followed by a moderately positive R wave. Einthoven's law. Einthoven's law states that if the electrical potentials of any 2 of the 3 limb ECG leads are known at any given instant, the third one can be determined mathematically by simply summing the first two. But note that the positive and negative signs of the different leads must be observed when making this summation. Typically, Einthoven's law is written as follows. Lead 2 equals lead 1 plus lead 3. For example, if in some model in the first lead according to Einthoven a potential difference of minus 2 mV is recorded, and in the third lead plus 1 mV, in the second lead the potential difference should be equal to minus 1 mV. Lead 2 equals minus 2 plus 1 equals minus 1 mV. Next example. Plus 3 mV are registered in the second lead, plus 4 mV in the first lead. What potential difference is recorded in the third lead at this moment? Lead 2 equals lead 1 plus lead 3. Lead 3 equals lead 2 minus lead 1. Lead 3 equals 3 minus 4 equals minus 1 mV. Solve the following problem. Minus 2 mV are registered in the lead 2. Minus 3 mV in the lead 3. What potential difference is recorded in the lead 1 at this moment? Solution. Lead 2 equals lead 1 plus lead 3. Lead 1 equals lead 2 minus lead 3. Lead 1 equals minus 2 minus minus 3 equals plus 1 mV. Solve the following problem. Solution. Lead 3 equals lead 2 plus lead 1. Lead 3 equals minus 3 minus minus 2 equals minus 1 mV. Answer, minus 1 mV. There are Kirchhoff's current law and Kirchhoff's voltage law. Einthoven's law is a corollary of Kirchhoff's voltage law. This law, also called Kirchhoff's second law, or Kirchhoff's loop rule, states the following: the directed sum of the potential differences, voltages, around any closed loop is 0. V1 plus V2 plus V3 equals 0. Taking into account the direction of the axes in the Einthoven triangle, Kirchhoff's second law look like this. V1 minus V2 plus V3 equals 0. Or V2 equals V1 plus V3. Or lead 2 equals lead 1 plus lead 3. Question. Einthoven's law is correctly written as follows. Lead 2 equals lead 1 plus lead 3. Can you write Einthoven's law like this? R2 equals R1 plus R3. In literature and on the internet you can often find this way of writing this law. Is this right? Let's do some research on this issue. Let's take an electrocardiogram from Wikipedia. Let's measure the amplitude of the R waves in leads 1, 2, and 3. R1 equals 3 mV. R2 equals 9 mV. R3 equals 6 mV. In this case it is really R2 equals R1 plus R3. Can this be considered Einthoven's law? Let's check this in other electrocardiograms. Let's study another electrocardiogram. Let's measure the amplitude of the R waves in leads 1, 2, and 3. R1 equals 10 mV. R2 equals 9 mV. R3 equals 6 mV. In this case R1 is not R1 plus R3. Therefore, the formula R2 equals R1 plus R3 cannot be considered Einthoven's law. Remember, Einthoven's law can be applied to any part of the ECG, not just the R wave. However, for the same moment. P.S. If the tops of the R waves are fixed at the same moment, then R2 is equal to the sum of R1 and R3. If we know what the ECG looks like in two leads, we can easily calculate what the ECG looks like in the third lead using Einthoven's law. In the figures, ECGs are presented both graphically and in table form. Solve the following problem. At moment 5. Plus 0.3 mV is recorded in lead 1. What is being recorded in lead 3 at this moment? Use a figure to solve the problem. Solution. At time 5, the amplitude of the ECG in leads 1 and 2 is the same and equal to plus 0.3 mV. According to Einthoven's law, lead 3 is equal to lead 2 minus lead 1, which is equal to 0.3 mV minus 0.3 mV, which is equal to 0 mV. Answer, 0 mV. Solve the following problem. At moment 4, plus 0.2 mV is recorded in lead 2. What is being recorded in lead 3 at this moment? Use a figure to solve the problem. Solution. At time 4, the ECG amplitude in lead 2 is 0.2 mV, 2 boxes. This means that 1 box is equal to 0.1 mV. Then the amplitude of the ECG in the lead 1 is 0.4 mV, 4 boxes. According to Einthoven's law, Lead 3 equals lead 2 minus lead 1 equals 0.2 minus 0.4 equals minus 0.2. Answer: in lead 3, minus 0.2 millivolts is recorded. See at the figure. Vector cardiography and electrocardiography. Two sides of the same coin. Vector cardiography, sometimes abbreviated as VCG, is a method of recording the magnitude and direction of the electrical forces that are generated by the heart by means of a continuous series of vectors that form curving lines around a central point. Was developed by E. Frank in the early 1930s. The instantaneous mean vectors have not a starting or ending location, A. Therefore, we can put the starting points of all of the vectors in one arbitrary point, B. Draw a line through the ends of the instantaneous mean vectors, C. This line is called the VCG loop, D. Note: VCG loop reflects the change in the magnitudes and directions of the instantaneous mean vectors. Note: VCG loop does not reflect the order of passage of excitation on the myocardium. VCG loop reflects the change in the magnitudes and directions of the instantaneous mean vectors. Normal vector cardiogram have three loops: P loop, QRS loop, T loop. ECG is a time-based sweep VCG on axis of lead. The time-based sweep of VCG on the axis of 1 and 3 leads. The figure, bottom right, shows the projection onto the frontal plane of the VCG loop, A, B, C, D, E, F, G, A. Let's do a time sweep of this VCG loop along the axis of lead 1 and lead AVF. The time sweep of the VCG loop along the axis of lead I and lead AVF. I want to show the time sweep of the VCG loop step by step. If instantaneous vectors are not determined on the VCG and point A, red, is recorded, isoelectric lines, red, to point A are recorded in the leads. Let's assume that we are studying the QRS loop of VCG. In this case, the VCG beginning of the loop, red line, is fixed in the negative areas of the leads and forms the beginning of wave Q, red lines, in both leads. Do not forget, the electrocardiograms in the figure are arranged in accordance with the VCG. Therefore, in the lead AVF, the negative waves Q and S are located above, and the positive wave R is located below. Later we will reverse this lead. Do not forget, the electrocardiograms in the figure are arranged in accordance with the VCG. Therefore, in lead 1, the negative Q and S waves are located on the left, and the positive R wave is located on the right. Later we will rotate this electrocardiogram 90 degrees counterclockwise. The final part of the segment of VCG forms the ascending part of the Q wave in lead 1 and completes the formation of the descending part of the Q wave in lead AVR. The described sections of the curves are colored red. The VCG segment BC forms the beginning of the ascending part of the R wave in lead 1 and the ascending part of the Q wave in lead AVR. The described sections of the curves are colored red. The segment CD, VCG, forms the end of the ascending part of the R wave in lead 1 and the beginning of the ascending part of the R wave in lead AVR. The described sections of the curves are colored red. The segment D, E, VCG, forms the beginning of the descending part of the R wave in lead 1 and the ending of the ascending part of the R wave in lead AVR. The described sections of the curves are colored red. The segment E, F, VCG, forms the ending of the descending part of the R wave in lead I and the beginning of the descending part of the R wave in lead AVR. The described sections of the curves are colored red. The segment F, G, VCG, forms the descending part of the S wave in lead 1, and the ending of the descending part of the R wave in lead AVR. The described sections of the curves are colored red. The segment G, A, VCG, forms the ascending part of the S wave in lead 1, and the S wave in lead AVR. The described sections of the curves are colored red. The instantaneous vectors are not determined on the VCG and point A, red, is recorded. Isoelectric lines, red, from point A are recorded in the leads. Thus, we made a time sweep of this VCG loop along the axis of lead, I, and lead, AVF. Let's rotate the electrocardiogram vertically. In this form, the ECG machine records the ECG in lead AVR. Wave Q is A, B, C segment. Wave R is C, D, E, F, G, segment. Wave, S, is, G, A, segment. Let's rotate the ECG 90 degrees counterclockwise. In this form, the ECG machine records the ECG in lead 1. Wave, Q, is, A, B, segment. Wave, R, is, B, C, D, E, F, segment. Wave, S, is, F, G, A, segment. In this form, the ECG machine records the ECG in lead 1 and lead AVF. The mean electrical axis. The mean electrical axis. Synonyms. Mean QRS vector. Principal vector of ventricular depolarization. In Russia they use the term electrical axis of the heart. The mean electrical axis represents the sum of all the mean electrical vectors occurring during ventricular depolarization. The mean electrical axis is depicted by a green arrow in the figure. The figure also shows the same instantaneous mean vectors, red arrows, as in the previous figure, but superimposed upon the axial reference system. In this example, the mean electrical axis is approximately plus 40 degree. The mean electrical axis approximates VCG. The mean electrical axis is located a three-dimensional space. However, as a rule, the position of the projections of the electrical axis of the heart in one of the planes is taken into account, most often in the frontal plane, 2D. The vector cardiogram during ventricular depolarization, the QRS vector cardiogram, shown in figure is that of a normal heart. Note from this vector cardiogram that the preponderant direction of the vectors of the ventricles during depolarization is mainly toward the apex of the heart. Determining the electrical axis from standard lead electrocardiograms. Plotting the M.E.A. of the ventricles from two ECG leads 1 and 3. Note. Clinically, the electrical axis of the heart usually is estimated from the standard bipolar limb lead electrocardiograms rather than from the vector cardiogram. Figure shows a method for doing this. After recording the standard leads, one determines the net potential and polarity of the recordings in leads 1 and 3. In lead 1 of figure, the recording is positive, and in lead 3, the recording is mainly positive but negative during part of the cycle. If any part of a recording is negative, this negative potential is subtracted from the positive part of the potential to determine the net potential for that lead, as shown by the arrow to the right of the QRS complex for lead 3. Then each net potential for leads 1 and 3 is plotted on the axes of the respective leads, with the base of the potential at the point of intersection of the axes, as shown in figure. If the net potential of lead 1 is positive, it is plotted in a positive direction along the line depicting lead 1. Conversely, if this potential is negative, it is plotted in a negative direction. Also, for lead 3, the net potential is placed with its base at the point of intersection, and, if positive, it is plotted in the positive direction along the line depicting lead 3. If it is negative, it is plotted in the negative direction. To determine the vector of the total QRS ventricular mean electrical potential, one draws perpendicular lines, the dashed lines in the figure, from the apices of leads 1 and 3, respectively. The point of intersection of these two perpendicular lines represents, by vectorial analysis, the apex of the mean QRS vector in the ventricles, and the point of intersection of the lead 1 and lead 3 axes represents the negative end of the mean vector. Therefore, the mean QRS vector is drawn between these 2 points. The approximate average potential generated by the ventricles during depolarization is represented by the length of this mean QRS vector, and the mean electrical axis is represented by the direction of the mean vector. Thus, the orientation of the mean electrical axis of the normal ventricles, as determined in figure, is 59 degrees positive. The angle alpha is the angle between positive part of axis of lead 1 and mean electrical axis of heart. This indicator, term, is used in Russia. The angle alpha reflects the position of the projection of the mean electrical axis on the frontal plane. The angle alpha reflects general view of the ECG in limb leads. The angle alpha is positive if we count it clockwise. The angle alpha is negative if we count it anti-clockwise. Determining the electrical axis from standard lead electrocardiograms. What is the position of the mean electrical axis of the heart, alpha angle, considered normal? There are different opinions. Although the mean electrical axis of the ventricles averages about 59 degrees, this axis can swing even in the normal heart from about 20 degrees to about 100 degrees. Guyton. From -30 degrees to +100 degrees. From -30 degrees to +90 degrees. From 0 degrees to +90 degrees. In Russia, from 0 degrees to +90 degrees. In Russia. Normal position, from +30 degree to +70 degree. Horizontal position, from 0 degrees to +29 degree. Vertical position, from +71 degree to +90 degree. Left axis deviation, less 0 degrees. Right axis deviation, more +90 degree. Methods for determining the position of mean electrical axis of the heart. Methods for determining the position of mean electrical axis of the heart. Graphical method. Table and chart method. Visual determination, degree method. Quadrant method. Graphical method. The value of the algebraic sum of each wave of one ventricular QRS complex is measured in millimeters, taking into account that the Q and S waves have a minus sign, since they are below the isoelectric line, and the R wave has a plus sign, plus. The positive or negative value of the algebraic sum of the QRS waves on an arbitrarily selected scale is plotted on the positive or negative part of the axis corresponding lead in the 6-axis Bailey coordinate system. These values, corresponding to the algebraic sum of the amplitudes of the waves, actually represent projections of the desired electrical axis of the heart on axes 1 and 3 of standard leads. From the ends of these projections, perpendiculars to the axes of the leads are restored. The intersection point of the perpendiculars is connected to the center of the system. This line is the electrical axis of the heart. Graphical method. The value of the algebraic sum of each wave of one ventricular QRS complex is measured in millimeters, taking into account that the Q and S waves have a minus sign, since they are below the isoelectric line, and the R wave has a plus sign, plus. The positive or negative value of the algebraic sum of the QRS waves on an arbitrarily selected scale is plotted on the positive or negative part of the axis corresponding lead in the 6-axis Bailey coordinate system. These values, corresponding to the algebraic sum of the amplitudes of the waves, actually represent projections of the desired electrical axis of the heart on axes 1 and 3 of standard leads. From the ends of these projections, perpendiculars to the axes of the leads are restored. The intersection point of the perpendiculars is connected to the center of the system. This line is the electrical axis of the heart. Methods for determining the position of mean electrical axis of the heart. Degree method for visual determining angles alpha. Visual method allows to determine the angle alpha with an accuracy of 8 to 10 degrees. The principle of the method is simple. 1. If the vector is perpendicular to the lead axis, the projection is 0. This is the so-called zero or isoelectric lead. Flashlight on the left. 2. If the vector is parallel to the lead axis, the projection of the vector is equal to the vector. Flashlight on the right. 3. The smaller the angle between the vector and the abduction axis, the larger the projection. And vice versa. Degree method for visual determining angles alpha. To use this method, follow these steps. Review all 6 leads, and identify the one that contains either the smallest QRS complex or the complex with an equal deflection above and below the baseline. Use the hexaxial diagram to identify the lead perpendicular to this lead. Degree method for visual determining angles alpha. For example, if lead 1 has the smallest QRS complex, then the lead perpendicular to the line representing lead 1 would be lead AVF. After you've identified the perpendicular lead, examine its QRS complex. If the electrical activity is moving toward the positive pole of a lead, the QRS complex deflects upward. Isoelectric, 0, lead is AVL. Lead perpendicular to AVL is 2, in this lead the wave amplitude is the largest, positive, wave R. The ECG formula. In lead 2 the amplitude of the R wave is greater than in AVR, S wave, and in AVF, R wave. The amplitudes in AVR, S wave, and in AVF, R wave, are equal and greater than in lead 1, R wave, and in lead 3, R wave. Amplitudes in lead 1, R wave, and in lead 3, R wave, are equal. Male lies on the positive part of the axis of lead 2 or is parallel to the axis of this lead. The angle between the positive part of lead 1 and the positive part of lead 2 is 60 degrees. So the alpha angle is 60 degrees. Isoelectric, 0, lead is AVL. Lead perpendicular to AVL is 2, in this lead the wave amplitude is the largest, positive, wave R. The ECG formula. In lead 2 the amplitude of the R wave is greater than in AVR, S wave, and in AVF, R wave. The amplitudes in AVR, S wave, and in AVF, R wave, are equal and greater than in lead 1, R wave, and in lead 3, R wave. Amplitudes in lead 1, R wave, and in lead 3, R wave, are equal. Male lies on the positive part of the axis of lead 2 or is parallel to the axis of this lead. The angle between the positive part of lead 1 and the positive part of lead 2 is 60 degrees. So the alpha angle is 60 degrees. Isoelectric, 0, lead is AVR. Lead perpendicular to AVR is lead 3, in lead 3 the wave amplitude is the largest, negative, wave S. The ECG formula. In lead 3 the amplitude of the S wave is greater than in end AVL, R wave, and in minus AVF, S wave. The amplitudes in end AVL, R wave, and in minus AVF, S wave, are equal and greater than in lead 2, S wave, and in lead 1, R wave. Amplitudes in lead 2, S wave, and in lead 1, R wave, are equal. A lies on the negative part of the axis of lead minus 3 or is parallel to the axis of this lead. The angle between the positive part of lead 1 and the negative part of lead 3 is minus 60 degrees. So the alpha angle is minus 60 degrees. Quadrant method. This chart will help you quickly determine the direction of a patient's electrical axis. Just observe the deflections of the QRS complexes in leads 1 and AVF. Then check the chart to determine whether the patient's axis is normal or has a left, right, or extreme axis deviation. A quick way to estimate the axis of the heart is to examine the direction of the QRS complex in leads 1 and AVF. Lead 1 is positive, wave R. Lead AVR is positive, wave R. Mean electrical axis is normal. Thank you for attention.